Yeah, welcome to the course on electrical machines 2. In this course, we will primarily focus on three-phase induction motors, starting from its basic operations, and then single-phase induction motors, and then synchronous motors. Anyway, before going to three-phase induction motors, it is essential to have some knowledge on windings on electrical machines. That we will be doing before I start three-phase induction motors. And before that, of course, we will discuss about the basic principles of any rotating machines, basic operating principles of any rotating machines. We will see that there is some common underlying principles which govern the operations of all the kinds of standard electrical motors, be it DC motors, be it three-phase induction motors, be it single phase or three-phase synchronous motors. So, the study will center around the steady state performance analysis of those machines in somewhat detail. Before, of course, I thought that essentially what you will see that when we study any type of electrical motors, we will try to draw its equivalent circuit and then analyze that circuit to predict the performance of that particular machines. Since the course is on electrical machines too, it is presumed that you have undergone a course on transformers and DC machines. Although DC machines is somewhat difficult at its constructional level, but nonetheless generally the electrical machine 1 course centers around transformer and DC machines. If time permits, I will also touch upon some interesting aspects of DC machines as well. Therefore, the course begins with electrical machines 2, and as I told you, equivalent circuit is one of them. So, let us not leave a transformer in its totality, because the equivalent circuit of the transformer you must be remembering. We will start from that, assuming you have undergone a transformer course, but I will try to arrive at the equivalent circuit of a transformer from the viewpoint of circuit analysis. And before that, if I want to derive the equivalent circuit of transformer, which you must be knowing it is drawn like this. And this transformer, let us assume it has got no core loss. So, that parallel resistance I have not drawn, and this is how it is drawn: R 1 X L 1, this is the what is known as magnetizing inductance J X M, and this is S square R 2, and this is S square X L 2, where X L 1, X L 2 are called leakage reactances of the transformer, R 1, R 2 are winding resistances of primary and secondary side, and A is the ratio of number of turns N 1 by N 2, where primary side is that side where source has been connected, that is here V 1. Okay, this equivalent circuit must be familiar to you, and it has been derived based on some physical considerations of the leakage flux, mutual flux and so on. And these impedances, R 2 is the actual secondary winding resistance, X L 2 is the actual secondary leakage reactance. These are to be multiplied by a square in order to draw the equivalent circuit referred to what is known as primary side. Similarly, the equivalent circuit can be drawn referred to the secondary side as well. But now, as I told you, this equivalent circuit we will try to arrive at by purely from the consideration of circuit analysis. After all, a transformer is nothing but a collection of two coils which are magnetically coupled, is not. So, this is the transformer core, this is the primary coil, say this is the secondary coils, and these two coils have got their separate identities with terminals brought out. And if you look at this configuration, you will immediately notice that these two coils have mutual coupling between them, because if one coil passes current, flux will be created, it is going to link the others and thereby inducing a voltage in the other coil. The number of turns of the primary is N 1 and that of the secondary is N 2. It is like this. Now, a coil has got also a self inductance, and how to find it out? Suppose you concentrate on one coil. This part I will do rather quickly. Suppose this is a coil and I want to find out its inductance. Now, to find out the inductance of a coil, we start from the fundamental definition of inductance. Inductance of a coil is flux linkage with the coil per ampere per 1 ampere. If it is carrying current I divided by I. Now, what is flux linkage? Flux linkage is if you pass a current I 1 through coil 1, it is going to produce a flux like this. This is phi. So, this N 1 into phi divided by I 1 is called the inductance of the coil. Now, in a transformer what happens is this, the flux which will be created when a coil carries a current, if I draw this portion in a bigger way, it will be like this. This is the core, this is the turns. There will be some flux which will be confined to the core, and that I call phi m, mutual flux, and there will be some flux lines which will complete their path through the air gap, and this is called leakage flux. But the definition of inductance says that it is the total flux linkage, okay? Total per unit ampere. So, if I say that I have energized coil 1 by current I 1 and total flux created by it, I will write it like this, phi T 1 is the total flux. Then this total flux will comprise in fact it consists of two pieces. One is the mutual flux phi m1 plus phi L1, the leakage flux. So, if it is coil 1, it is carrying I1 current. So, phi m1 and phi L1 together is your phi T1. This is the total flux linkage, this one. Therefore, by definition, inductance, self inductance of the coil will be flux linkage with the coil. So, N1 into phi M1 plus leakage flux phi L1 divided by I1, and this can be broken up into two terms as N1 phi M1 by I1 plus N1 phi L1 by I1, is it not? So, this is the thing. Now, this part which is not confined to the core, that is the iron material of the arrangement, is called the leakage inductance. This is also an inductance because N phi by I. So, this is written as N 1 phi m 1 by I 1 plus this I will write it as L 1, that is the leakage inductance of the coil, leakage inductance. So, this is what this L 1 means. Therefore, self inductance of a coil, if you want to find out, you have to consider the total flux, which consists of two parts, that is phi m1 the flux which will be within the magnetic material, and phi L1 is the flux which crosses or closes its path largely through the air gap. Okay. So, this is the leakage flux. So, I think we have understood what self inductance means. So, this is page 1. Now, coming back to the transformer, we have now got two coils instead of a single coil. So, once again I mean referring to this coil, this is one coil, this is another coil. So, suppose we say that, let me redraw it, it is better. This is the core and these are your coils. See, while drawing the coil, I have drawn it rather in detail, showing its sense of the winding. Okay. I have not drawn it like this, never draw like that, better draw in this fashion, and this is the another coil. This has got number of turns N 2, this has got number of turns N 1, and this is the core. Now, let us imagine I have only energized the primary coil with a DC current I 1. Okay. Then, as I have told you, there will be flux created, which will have two components phi m1, and there will be flux lines linking only this winding, that is called leakage flux phi L1, and based on that I have defined in the previous page L1 to be N1 phi M1 by I1 plus L L1. This is the self inductance of the coil. Now, what is the mutual inductance? When there are two or more coils sharing a common magnetic circuit, then if any of the coil carries current, there is going to be flux linkage with the other coils. So, in this case is very simple, two coils are there, one coil is carrying current and it is this mutual flux phi m 1 that is going to link the second coil N 2. Phi L 1 after all cannot link the second coil, and this is therefore, I can define mutual inductance like this M 2 1 as flux linkage with the second coil with N 2 divided by 1 ampere flowing through coil 1. Once again, the unit of M will be same as L Henry, that is flux linkage Weber turns per ampere. So, this is flux linkage with N 2 divided by I 1. Second coil I have not touched, nothing is flowing through the second coil. So, this is called the mutual inductance of the second coil. The second suffix indicates that the first coil is carrying current. So, this will be flux linkage with N 2 by I 1, and this is obviously the flux linkage with N 2 because of I 1 is nothing but N 2 phi m 1 divided by I 1, is it not? This will be the value of M 2 1. So, this is the mutual inductance when coil 1 carries current, coil 2 nothing is doing, and you get M 2 1 and L 2 1. These are the two things you get. Now, let us say I am once again redrawing the circuit and I am telling that this time what we will do is this, I will pass some current through the second coil, let it be constant current, okay, DC current I 2 and N 1, and this coil I keep it open, nothing is connected. This is N 2, sorry, this is N 1, and you pass a current like this. If you pass a current in this direction, as you can see the flux produced, you can show the direction of the current if you draw in this particular way as I told you, and decide about the direction of the flux. So, flux will be once again clockwise and it will be like this, is not, and this flux once again the total flux created by secondary coil, second coil I will write it as phi 2 t, and it in the same way can be broken up into two terms. One is the mutual flux phi m, and this time I will write 2 because coil 2 is carrying current and it has created the flux. So, phi m 2 is the mutual flux which is confined to the core, and there will be a component of flux which will complete its path largely through the air gap, and that will be termed as phi L 2. In the same way as we have done in the case of the first coil. So, same explanation goes, this is the total flux created by coil 2, it is carrying a current I 2, and the total flux is nothing but sum of mutual flux plus the leakage flux. So, this is this. Therefore, the inductance, self inductance of the second coil will be once again the flux linkage with the second coil, total flux linkage phi 2 t per unit ampere, that is I 2, self inductance of the second coil. And this can be, after you put these two things here, it can be broken up into N 2 phi m 2 divided by I 2 plus N 2 phi L 2 divided by I 2. So, the self inductance of the second coil will be this term N 2 phi m 2 by I 2, and this term I will call leakage inductance of the second coil L L 2. This is how these things comes. Now, this is this. So, L 2 is this one. So, let us go to third page. So, recall that now I am not going to draw, but what results I have got till now is L 1 is equal to N 1 phi m 1 by I 1 plus L L 2, and L 2 self inductance of the second coil is N 2 phi m 2 by I 2 plus L L 2. This is 1 leakage inductance 1. These are the two things, and I told you inductance, mutual inductance in this case M 2 1 is nothing but N 2 phi m 1 by I 1. Similarly, I can define the mutual inductance when second coil is carrying current. So, I will write it as M 1 2. This is the flux linkage with the first coil N 1, and the mutual flux this time is phi m 2 and divided by per unit ampere flowing in the second coil divided by I 2. This will be the thing. Okay, fine. Now, let us concentrate on these two equations here. Your these two coils, mind you, they are sharing a common magnetic circuit. Okay. So, what will be the flux? We have done magnetic circuit analysis. If a coil is energized, how to calculate the flux inside the core? If I assume it is a linear magnetic circuit, phi m 1 will be nothing but mmf divided by reluctance. In this case, when coil 1 is energized, mmf is N 1 into I 1 and divided by the reluctance. Reluctance of what? Reluctance of this flux path, which completes its path in the core. So, this curly R is the reluctance. Similarly, phi m 2 will be nothing but mmf. In this case, I am only energized second coil in the second row. So, this is N 2 I 2 by the reluctance. So, this is the thing where reluctance I am assuming it to be constant and assuming linear magnetic circuit. So, I can always calculate the reluctance of the magnetic circuit. You know, it is like 1 by mu 0 mu r L mean by A cross section. I am not going into all those details, but I know that flux is MMF by reluctance, MMF is N into I divided by reluctance. So, I have got this. Now, let me play with these two equations. What I will do is this M21, I will, it is already obtained as N2 phi M1 by I 1. This is the thing. Is not N2 phi M1 by I M1, and M12 is this one. Now, what I will do is this, I can write it as N2 by I 1 and phi M1, from this I will plug in this phi M1 here. N2 by I 1 is N1 I 1 by reluctance, where I 1 goes, and it is nothing but N1 N2 by reluctance. Similarly, M12, if you calculate, it is from this, it is N1 phi M2 by I 2, but phi M2 is nothing but this. So, put it here. So, you will be getting N1 by I 2 into phi M2 is N2 I 2 by reluctance. I 2 goes, and it is equal to N1 N2 by reluctance. So, what is the conclusion? M12 is equal to M21. This is a very important thing. There is no reason to distinguish between these two, provided these two coils share the same magnetic circuit. So, and therefore, the mutual inductance can be represented by a single number m, not M12, no suffix I will write. Of course, for self and mutual inductance, we have to use L1 and L2. Therefore, what we have done till now in this unit, as I have told you, my target goal will be to derive the equivalent circuit of a transformer, looking at it as in terms of self and mutual inductances, and try to get this equivalent circuit, where I have assumed that the transformer is having no core losses, that is hysteresis and eddy current losses, whether such an equivalent circuit can be arrived at using the circuit concept and using the concept of inductances. So, more in the next unit. Thank you.